Hi, everybody. Welcome to Coronavirus Diaries, day 376, or so it seems. As you can see, I've completely foregone any idea that I might be an authority figure, and I've stopped showering, and my hair is, doing all this stuff. Um, yeah, welcome back. Today, we are going to kick off the material that we're going to be covering for the rest of the semester, which is actually not all that long. So we got cut a little short this semester because of global pandemics, but we're still going to have a few weeks now to talk a little bit about climate change and also what we can do about it going forward, and how a lot of the topics in this class that we've covered so far um, seem adjacent to climate change, but actually they're front and center. So I want to start off just by reminding you what we've been talking about. So this is a figure from your book that we talked about a long time ago. It's out of date. It's a 2010 figure, but it's still surprisingly accurate, given how much we've changed. You'd think this would be less accurate than it is right now. It's 10 years old. Um, right, 85% of worldwide energy consumption comes from fossil fuels, or thereabouts, around in that ballpark. Um, Fossil fuels are in virtually everything that we do. And when you burn fossil fuels, one of two necessary byproducts of fossil fuel combustion, I hope you all know this by now. If not, write it down and memorize it. It'll be on a test. It already has been on a test. Is necessary byproducts of fossil fuel combustion: water vapor, not a big deal; carbon dioxide, the main reason that we have a global warming problem. So 85% of our infrastructure, of our energy consumption, that's driving our car, turning on the lights, everything, flying on an airplane, comes from doing things that release carbon dioxide into the air. Renewables are a very small part of the energy mix. So carbon neutral things like solar and wind are a really small part of our energy mix. So in 2010, you can see they fell into this little sliver of other. This is bigger than it was in 2010, but it's not more than 2% now. But what it's doing is it's growing exponentially. We all have way more experience looking at exponential growth now than we did a few weeks ago, because another example of exponential growth is, of course, the coronavirus. So, right, every few years, the amount of renewables that we have is doubling. That's not fast enough to deal with the climate crisis as it is right now, but it is a big part of what's going on. Fossil fuels are also in short supply, especially oil. So we have tons of coal. We've got a pretty decent supply of natural gas, at least for the next few decades, especially if you consider fracking. But they are finite resources. For everything but coal, we will certainly run out, if not very close to out, in our lifetimes. So it's time to be planning for the future, independent of whether you're concerned about a global warming problem. Fossil fuel extraction damages the environment, pollutes the air, and kills people. Right, and we've spent a lot of the class talking about the environmental impacts of fossil fuel combustion. And, I think it's not an unreasonable statement to make to say that, geez, I'll go with most of the pollution impacts that we experience in our lives are a consequence of fossil fuels. So almost all of the air pollution in the air is because of fossil fuel burning. Specifically, coal burning is by far the dirtiest. And so before class today, I had you watch this video that shows what has happened in this global recession that we find ourselves in. So concentrations of pollutants that are produced when you drive your car, fly in an airplane, do things that a normal functioning economy does. Those concentrations are way down. So the crisis in China started last fall. So we have several months of data for China just showing, actually, not that it is a good thing that we have the coronavirus right now, but actually the number of lives saved due to lack of air pollution in the air in the last few months is enormous. And so, maybe rather than thinking the coronavirus is a good thing, what we can think about is, well, geez, moving forward, we have a real opportunity to save lives by polluting our air less, by getting our energy from fossil-free sources like solar and wind. So the main take-home point that I hope you have from all of the weeks of the class that we've done thus far is that, right, while there are these problems with our current industry, energy industry, right, reducing our emissions will require systemic change to virtually every aspect of the developed world. Right? It's 85% of our energy right now. Okay, it does not allow developing countries the luxury to grow the same way that the U.S. did. Right, so the U.S. is at the top of the world in terms of their quality of life that they get to enjoy for energy consumption. And it is certainly not our place to tell developing countries like China, India, poorer countries like most of the continent of Africa, lots of countries in South America, all over the world. There's more developing and undeveloped poor countries than there are rich countries like us. They can't develop the way that we developed in a fossil fuel, carbon intensive way. They have to develop in a cleaner way. And moving forward into that direction, the reason that they can't do that is because if everybody had the quality of life of the U.S. with the carbon intense life of the average person in the U.S., then the climate problem would just be completely out of control. Okay, so that lays the foundation for where we are and where we've been with this class so that we can talk about the climate. So I have 3 topics that I want to cover in these next 3 digital classes. So the first topic is right now, we're going to talk about, is it warming up? So we're going to look at the global temperature record and we're going to analyze the extent to which it's warmed and whether that's something that has affected us and how it has affected us just in terms of observation. So not looking forward decades ahead, just right now. Has it warmed? How much? How meaningful is that warming? After that, we'll talk about why it's warming up. So we'll talk about the greenhouse effect in a pretty hand-wavy way, but I think a way that, at least for me, helps me understand the main things that lead to why carbon dioxide and other greenhouse gases in the atmosphere cause a warming. And then we'll look at the fluctuations in the observational record of carbon dioxide. After that, we will talk about some impacts of warming. And of course, we don't have time in this class. This is not a climate change class. We don't have time in this class to kind of survey all of the impacts of the warming. So I'm going to focus in on the Arctic because the Arctic, while not near us, is really ground zero for some of the changes that have already occurred. So warming in the Arctic is more, the Arctic, that's north of here, right? So think about northern Canada, Russia, the North Pole, Greenland, places like that. Alaska, I think, would be the only place in the US that qualifies as the Arctic. So the changes that have happened there have just been massive. So we're going to focus in on pointing out a few of the more visual overviews of the Arctic. Okay, so this is the global thermometer record, and it dates all the way back to the 1880s. So that is the year that we have decided we had enough of a global thermometer record. We have kind of thermometers on all of the continents all over the world that took long-term records. We can say that's the first year that we had a thermometer record for what the temperature of the planet is. So blues here are colder than normal, reds are warmer than normal, and you can see a pretty obvious trend going from mostly blues down here in the beginning of the record up to mostly reds up here in the end of the record. This is plotted as anomaly data. So if you look actually here, the line in the middle is actually 0 degrees Fahrenheit. That's not to say that the temperature of the planet was 0 degrees on average. That's a way that we can say that all positive numbers, so all of these numbers here on the y-axis, are years where the temperature was warmer than normal, and all blues here are years where the temperature was colder than normal. Anomalies are really nice to look at rather than total temperatures, and let me give you an example, right? if I told you that the temperature in February, I'm going to make up this number because I didn't look it up before class, but I told you the temperature in February on average was 30 degrees Fahrenheit. Um, to me personally, and I study the climate, that's not a very useful number because I don't know if that's hot or cold or normal or abnormal. So if I told you, but if I told you that the temperature in February was 5 degrees warmer than normal, then that's meaningful information to you. Okay, so an anomaly, that 5 degrees warmer than normal, or 0 degrees, it was right at normal, an anomaly tells you more meaningful information. So it's super common when we're talking about climate data like this to plot everything relative to zero. And so that's what that means. Okay, one thing I wanted to point out before I move on here is that there is this overall warming trend, but we've had decades where it cooled, even among this overall warming trend, right? So here's a decade in the 40s and the 50s. If you look at this, if I were to draw a line, there's actually a cooling trend for that decade. So it cooled for 10 years in the 1940s. So, right, individual years, individual decades, even, certainly individual storms are almost never examples of global warming. What we are talking about when we talk about the fact that it has warmed is this gradual, actually, it's not very gradual on an ecosystem type thing, but right, this decades long warming trend that has occurred, and it's not something that we are blaming on an individual storm or an individual event or really even an individual year. Okay, so a couple of take-home points, and I'm going to return to the slide a couple of times, but I just want to lay out some things that I hope you take away from this lecture slide, from this lecture presentation today, is like the difference between climate and weather, okay? So weather fluctuates 50 degrees Fahrenheit on some days. Actually, I'm going to show you in the next slide, Albany's difference between its maximum high and its maximum low is 100 degrees, okay? And if you go over here, we're talking about a warming of just a couple degrees, right? The largest temperature up here is 1.8 degrees Fahrenheit. The smallest down here is negative 0.9 degrees Fahrenheit. So we're just talking about a couple degrees of warming, okay? But day-to-day fluctuations, even from morning to night or one day to the next, can be 50 degrees on some days, okay? So when I first started learning about this, geez, I thought, why are we worrying about a few degrees? And I hope to convince you that a few degrees is meaningful. The first example that I want to give you about why a few degrees is meaningful is one that was on your reading quiz, right? In the last ice age, there was a 1 mile tall mountain of ice here in Albany, New York, where I sit delivering this thing to a little dot on my computer screen. It was only 6 degrees Celsius, that's about 10 degrees Fahrenheit, colder during the last ice age than it is now. So obviously this weather versus climate, this like day-to-day fluctuation in our weather is a very different and less meaningful thing to the climate system than sort of a decades or centuries long warming or cooling. And I will come back to this. Individual storms are rarely evidence of global warming in a little bit, but I don't want to talk about that yet. So a Mark Twain quote is, "Climate is what you expect, weather is what you get," right? So let's look at what our climate here is in Albany, New York. So the month of January in Albany, New York has as the average low 13 degrees Fahrenheit, and the average high is 31 degrees Fahrenheit. So that's a typical average low and an average high. Our record low was negative 28. Our record high was 71. And this is where I got that 100-degree temperature range. So in the month of January, we've had 100 degrees of range in temperature. We get an average precipitation of 2.7 inches and average snow of 18 inches. These obviously vary a ton from year to year, right? There's some years where there's almost no snow in January, and there's some years where we get 18 inches of snow in just 1 year. Okay, so the question here is, why are we worrying about a few degrees due to anthropogenic greenhouse gas emissions? And I love this word anthropogenic. It's a great way for you to sound smart when you're talking to your fellow peers or your parents. Anthropogenic is man-made, so that's a good vocab word. If you put it in a paper or an essay response to a test, I promise to be very impressed. So let's talk about the difference between weather and climate. Right, here is a 5-day forecast for our weather in January of 2019. This was not this January, but last January. It was the very first week of the semester. Maybe you remember Martin Luther King week. We had a forecast for snow. Here's what that forecast looked like, right? In Albany, New York, we got right in this range. This was a very good forecast event, right? 18 to 24 inches of snow in our backyard. It canceled classes for maybe a couple of days. I don't remember, right? That's our weather, right? Here's what that weather looked like from the same week this year in January. There was a little bit of a chance of rain and snow, but if you see, right, a chance of rain and snow, but a high of 39, it's not going to snow much if it's 39 degrees, right? And so rain overnight and a low of 34. This was a perfect example, actually, of a global warming type storm, right? So our weather was very different 2019 to 2020, but the climate doesn't change much in a year, right? Global warming, as we just saw, is this thing that extends over decades, right? It's not something that we are going to like inject a lot of carbon dioxide into the air and see a response immediately. It takes decades for those responses to really fully come into force. So this wasn't a change in our climate, this was a change in our weather. And actually, a really cool thing here is that the low on Saturday night was 34 degrees. It was 2 degrees away from being snow. If it had been 32, then we would have gotten a lot of snow on this night. And actually, this past winter, we've had a lot of events like that. Just these events that were mostly rain or slushy snow, and they were right above freezing, right? 100 years ago, if that snowstorm had hit when it was 2 degrees colder than it is today, right? 2 degrees doesn't seem like that much, but 2 degrees is the difference between the rain event that we had this week in January and a snow event that would have dumped a lot of snow and probably canceled classes. So there's a little example of how, right, these shifts in our climate might not seem very meaningful on a day-to-day basis, but they're actually really meaningful when you average them out over a time scale of climate. So let's talk about weather, climate, and climate change. Right. So what we are doing now is we are causing a climate change by putting greenhouse gases into the atmosphere. So the climate is getting warmer. So I have this like upward sloping trend here where I've tried to put on the x-axis the time. So here's earlier, here's today, and going into the future. And then on the y-axis, something like climate. So we'll have cold temperatures down here on the bottom and warm temperatures. Okay, so we have climate change that's occurring due to our greenhouse gas emissions. We also have natural weather variations. So I'm going to call this natural variability, right? Our variations from year to year in how the climate looks. And these mean that, right, we have warm years and cold years, right? So there's a very warm year, there's a very cold year. We have sort of cooling trends and warming trends that happen just in a normal, natural, uninfluenced by fossil fuel combustion kind of a climate. When we add those two together, what we get is something that looks like this, right? So if we look over here, we actually had a warm year toward the beginning of this record and a cold year toward the end of this record. But those are superimposed on this warming trend here. Okay, so we can have, and this is data that I made up. So this isn't real data, but I made this data up to try to show you how we can have warm years. We had warm years 100 years ago. And so we still have some records. And actually, if you look back here at Albany's record low, the record, well, I guess this more or less fits, but we have months in Albany where the record high is not a recent year. It happens to be for January, but we have 100-year-old hot records that have not been broken yet, right? Where it was still hotter 100 years ago. How is that possible? Well, we can still have record warm and record cold in a climate that's changing. So I wanted to talk a little bit about another example of this, which in the scientific community was called the hiatus. And so if you look here at our temperature, there was a period of about 10 years in the beginning of the 21st century where it didn't warm up. And there was a lot of speculation. There's probably 2,000 papers written on this hiatus, and it got a lot of press in the news media as evidence that global warming is a hoax and it's not really warming and what's going on. And really, what this was just natural variability. There was a few cold years that are pretty well understood. I won't get into the details of them. There was a few cold years that were colder than normal for pretty well understood reasons. And here's what happened right after 2014. There's the last 6 years and what they have done. So we had this period where there wasn't any warming, followed by a period where there was a lot warming, and this is just part of natural variability. These undulations of we have decades of cooling superimposed on this overall warming trend. So another example of a few degrees of warming in our weather, not about a big deal. What about our climate? So this is what it looked like in the last ice age. So we had over the top of us this Laurentide ice sheet. So all of Canada stretching down. We were really more or less the southernmost extent of the location of the Laurentide ice sheet, where there's just a block of ice that was a mile tall. And one way that we know that there used to be an ice sheet over us is we have evidence of these glacial erratics. So here's a pretty cool one that's down in the Catskills. Pyramid Mountain in northern New Jersey. They're also throughout the Catskills. This one just is somewhere else. So if you have a giant mountain of snow, what that giant mountain, well, we'll call it ice because it's ice. What that giant mountain of ice does is it pushes, and it's so giant that it can push these giant boulders here. And where the extent of the ice goes, so like right where the ice ends, it'll just leave those boulders. So it grabs a boulder, it pushes, and then it stops. And then right at the edge of the ice, there's these precariously balanced boulders that are called glacial erratics. And these glacial erratics mark the extent of where there used to be an ice sheet. And since we are right at the southern boundary of where an ice sheet used to be, glacial erratics are all over our region. And there's some pretty cool pictures of people who have done things on this tip tripod rock, right? It looks like this giant rock is just balanced on these tiny little things because it is, right? It's just balanced on these little rocks underneath here. There's somebody else doing something stupid, although it's probably not that stupid. There we go. So some take-home points from this that I wanted to follow up a little bit more on this climate versus weather. We already talked about the first one, the last ice age. So I also want to talk about things that on a normal 55-degree and sunny day in Albany, warming a few degrees, even in the future, isn't going to matter all that much, right? So the problematic events that are going to stress us the most are events that are already on the brink today. So I already gave you that example of the snowstorm that would have been a snowstorm if it was 2 degrees colder, right? So if it's 33 degrees, it rains. If it's 32 degrees, it snows, right? That's a big impact to our local world. Here in Albany, right, when it rains, that tends to have less of an impact on us, right? Unless you, right, like a snowstorm seems like it has all of these important impacts on us, right? It closes down school, it has these big economic impacts, people get stuck in the snow, and that's potentially like people can die, and lots of bad things can happen. But if you say study stormwater runoff, then maybe you know that if it rains, that water gets deposited into the rivers immediately. Whereas if it snows, then that water can stay up into the mountains. And so every spring we have these events where it floods because it rains, right? So transitioning to more rain actually can make issues for us from a stormwater runoff perspective. We also rely on melting snow water for some of our drinking water. That's a bigger deal in other places than it is here, but that's something that we do here. So if it's not snowing, then we don't have this reservoir of stored, clean, fresh water that we can take from and when it melts. So a lot of New York City gets its water from the stored sources. Other things to think about: timing of migrations, right? So a few degrees makes a big difference on when spring arrives. So when do birds fly south for the winter and north for the summer? Apple blossoms. So as the spring is coming earlier and earlier, apple blossoms are blooming earlier and earlier, and that actually can be positive and it can also be negative, right? So if the apple blossom blooms earlier, then a hard frost in the spring, that can still happen. So what's happened a couple of times in recent years is that we had an early apple blossom followed by a late spring frost. Right, spring frost is still going to happen, going even in a warmer climate, and that devastated some of the apple blossoms because like they had bloomed earlier than normal, and now they're kind of having to deal with the fact that it doesn't work anymore. Yeah, I already talked about snowmelt for flooding and water resources and stuff like that. So yeah, and so individual storms, individual years are all rarely evidence of global warming or global cooling, right? We can have a hot year 100 years ago, just like we can have a cold year, a colder than average year today. So we have seen cooling decades, even though the overall trend is warming. I will say that it's really just in the last 10 years or so that uh, some individual storms have been deemed to be so extreme that they were virtually impossible to imagine before the warming started. So like we're just barely starting to peek into this territory where weather events are different enough, extreme enough that we can see a human signature on them. And so here's that global temperature anomaly curve. It doesn't have the blues and the reds because it was made in a much less computer literate program, but we can still see right this global temperature anomaly trend going from the colder than normal in the 1880s up to today, and we see the temperature varying. So here is a trend line that I put in from the end of the what's that 19th century. Right, so if we take this trend, it's going down. And if we use that to make a forecast up to 2025, we just predicted global cooling. Right, we're going to be way colder in the future. If I look at these next few decades, I think I looked at the 1910s and 1920s. Geez, global warming in a big way. Obviously, that's not evidence of global warming or global cooling. That's just our natural climate variability, varying from year to year and decade to decade. Let's keep going. Oh, there's our decade in the 2040s where we had global cooling. Here we are in the 1970s where we had a decade where it was more or less not warming or cooling. There's another decade, that's the hiatus decade, where we had a 10-year in recent memory decade where there was no warming or cooling. And so here's where I mean down here on the bottom, right? Individual storms, individual years, rarely evidence of global warming or cooling, right? We've seen these cooling decades, even though the overall warming trend. But here's what's been happening in recent decades. So right here is this black line is what I get when I best fit line all of the black data points from 1880 up to today. And the red line is what I get when I do a best fit line from 1950s. And what I want you to see is actually the red line is steeper than the black line. Okay? So not only is it warming, but the rate of warming is increasing in recent decades. Now I'm going to put a trend from 1980. You see the green line is steeper than the red line. Now let's put a trend from 2010. The blue line is the steepest of all, okay? And so right, the rate of warming is increasing relative to what it used to be. So you put all this together and we'll say Earth's average surface temperature has warmed by 1.2 degrees Celsius. That's like 2.5 degrees Fahrenheit or so. Since measurements began, and most of the warming has actually been in the last 30 years. So I wanted to show a couple of visualizations of what the warming looks like. So let's get that up. So what this is going to do is step through beginning in the year 1900. And so we have on this, we have Asia, Africa, Oceania, America, and Europe. And the red things here, and actually on the outer axis, which you probably cannot read, are individual states, or individual countries, excuse me. But I want you to look at the undulations of the red and the blue here. So warmer than normal is red, and colder than normal is blue. And it starts in the beginning of the 20th century, and we'll just step through it. So what you can see is that in the beginning, we have heat waves and cold waves and they tend to be kind of continental scale. I'm actually going to start this over, and I want you to pay attention to that. So maybe I'll try to stop it. You never stop it when you, there's a good one, right? So here it was cold in all of Europe, but that's balanced out by warm in all of Africa, right? So we have regions where it's warm and regions where it's cold, but if you average over the whole planet, it tends to be, it's a wash, right? It's really rare to have a heat wave over the whole globe, right? We have these hot areas somewhere and the cold areas somewhere else. Now we're into the 40s. That was that decade of cooling, 50s, 60s. And now watch for what the heat wave pattern looks like. We have like the whole planet is now hotter than normal. And this ends in 2016. Let's watch one more. So now this is going to have blue be colder than normal and red is warmer than normal. And again, we see, right, we have large blobs of blue that are all together, but those are balanced out by large blobs of red that are all together. And the average over the whole world is that it's that those cold regions of cold and regions of hot kind of balance each other out. And there we are at the end of the record, where now we have almost all warming, but there are still, you know, a couple of spots where it's a little bit colder than normal. Okay. So here is some more of that data. So is it warming up? Here's the 10 warmest years on record, starting in 1880 and going to today. The warmest year was 2016, 2015, 2017, 2018, 2014, 2010, 2013, 2005, 2009, and 1998. These are all recent years, right? So 8 of the 10 warmest years are between 2013 and 2019, and every single one of them is, and just 8 of the 10 are all in these, like, what is that, 7 years. All of them are since 1998. And this doesn't include 2019, but I looked up 2019, and 2019 was the second warmest year on record, so it would slot in here between 2016 and 2015. Here's what the anomalies looked like. So month by month, right? Every single month was warmer than normal, right? So it's not that this was some big heat wave that happened in summer. It was that winter was warmer than normal. And if you want to think about winter being warmer than normal, well, geez, you know, ticks die in winter because it's cold. So winter being warmer than normal is something that causes ticks to die less. We get less snow because of that, right? Summer, winter, spring, fall, all over the continent is warmer than normal. But actually, if you look at this, and if you look at the central U.S., even though it was the second hottest year on record, there was pretty big cold anomalies here in the U.S. for much of the year, and those cold anomalies were balanced out by really big warm anomalies elsewhere. But right, even in this second hottest year on record, it's not hot everywhere all of the time. So I want to take a tour of some more of these impacts, but of course I can't show you everything, so I'm going to focus in on the Arctic, because that is warming faster than anywhere else in the world. And actually, if I go back to here, you can see, all right, the Arctic is this region here in the northern part of our climate. You can see that over here where it's gray, that is where there's no data. So we have a hard time, satellites have a hard time getting good records of temperature over the pole for reasons that I don't need to go into. But those would all be bright red here over the Arctic if there was data for that. Okay, so I'm going to watch a video here about what's happened with Arctic sea ice.
In 1978, satellites began continuously observing the polar regions, and the dynamic beauty of the Arctic sea ice was revealed. What we expect to be a solid mass of ice is actually in constant motion. As researchers continue to seek a deeper understanding of this region, new information about how sea ice changes is coming to light.
In this animation, we're taking Arctic sea ice into the third dimension. Here, we're looking at the ice age, which is an indicator of thickness. Generally, older ice is thicker ice.
That's the voice of Dr. Walt Meyer, senior research scientist at the National Snow and Ice Data Center.
What you see in this animation is the ice pulsing out and in with the seasons. In winter, the ice grows out and expands outward. In summer, it contracts inward as it melts. You see the whiter ice, which is the older ice, moving around the Arctic, being pushed around by winds and currents that move the ice. Over the years, the ice pulses around and moves around towards the top along the coast of Greenland. The older ice eventually moves out of the Arctic and into the North Atlantic, where it melts. The ice gets replenished within the Arctic because some of the ice survives each summer and grows older, and particularly in a region north of Alaska called the Beaufort Sea, where the ice spins around in a clockwise direction called the Beaufort Gyre. And that ice can keep spinning around oftentimes for several years and gradually getting older and thus getting thicker. Eventually, the ice will spin out of that gyre and go out through Fram Strait. In the past, we've always had enough ice growth and ice aging, enough ice surviving the summers to replenish the older ice that's lost. But in recent years, we've seen less replenishment. There's been more melt during the summer, so the ice that goes out through Fram Strait has not been compensated by the ice growth. In addition, especially in recent years, we've seen some pretty remarkable things in the Beaufort Sea, where that area that used to be a nursery for the development of the older ice allowed the young ice to age and mature. What we've seen instead is the ice is now more broken up, more scattered, and that's allowing the older ice to melt within the Beaufort Sea. So we're seeing the Beaufort Sea go from a nursery to a graveyard for older ice. As we get towards the more recent years, much of that oldest ice, the ice that's older than 5 years old and the bright white, has almost virtually disappeared from the Arctic Ocean. And the Arctic is now dominated by younger and thinner ice.
Okay. So another thing I want to talk about is how ice is melting up in the Arctic. So this is a figure from Greenland, and actually this is like a river of ice. So right, we have this ice, and this over here down here is the ocean. And so a part of natural processes is called glacial calving, where this river of ice is constantly being replenished by snow that falls up on the top of Greenland because it's very cold in Greenland. It sort of flows out this river, and then the chunks of ice fall into the ocean as part of this natural process. But this rate of glacier calving, so glaciers falling out off of land and into the ocean, and that's something that causes sea level rise. So you take land and ice that used to be on land and you deposit in the ocean, and the whole level of the water in the ocean will go up. Is speeding up. So let me show you that video.
Jim, nothing's happening.
Jim, it's going well. We had some serious bouts of wind, but other than that, things are fairly well set up here. We've got some continuous time lapse going.
It's starting, Adam. I think. Adam, it's starting.
Oh wait, Jim, this is the big piece is starting to cast. Let me call you back.
So this is some footage of a documentary that was being filmed that was looking at one of those rivers of ice coming off of Greenland. And so this is a zoomed in picture that you're looking at of the edge of that river of ice that's calving into the water, into the ocean.
Okay, bye.
Still going? Yeah. In that V section right there. Holy shit, look at that big bird rolling. All four are running, right?
Yeah. Look at that. You see how, look at the whole thing.
Skip forward a little bit. I want to not play this whole thing. You're welcome to go watch the whole thing at some point.
We'll resort to some illustrations again to give you a sense of scale. It's as if the entire lower tip of Manhattan broke off, except that the thickness, the height of it, is equivalent to buildings that are 2.5 or 3 times higher than they are. That's a magical, miraculous, horrible, scary thing. I don't know that anybody's really seen the miracle and horror of that. It took 100 years for it to retreat 8 miles from 1900 to 2000. From 2000 to 2010, it retreated 9 miles. So in 10 years, it retreated more than it had in the previous 100.
Okay. So this is a map of Greenland. So here's the pink here shows where Greenland was melting in 1992, and now here's where it shows where Greenland was melting in 2002. And I think the stuff that we just watched is a really visual example of how this should cause sea level rise. We're talking about massive, like, chunks the size of Manhattan of ice falling into the ocean. And right now, Greenland is accounting for about 25% of global sea level rise, just Greenland itself, just ice moving off of Greenland, melting off of Greenland, and falling into the ocean. So this is, I've talked about the Arctic. There's plenty of other ways that we know that that the world is warming, right? We have the sea level is rising, not just because Greenland is melting, right? We also have that as things heat up, they expand. So the ocean is actually just taking up more space because as it warms, it takes up more space, and that causes sea level to rise. The ocean is acidifying. When carbon dioxide gets into the ocean, it forms something called carbonic acid via a process that's really similar to what we talked about for acid rain. So right when sulfur dioxide gets into the water, it makes sulfuric acid. Just like when carbon dioxide gets into the water, it makes carbonic acid. And naturally occurring carbon dioxide in our air actually means that our normal rainwater is just a little bit acidic because of that. But this is accelerating as we have more and more carbon dioxide in the atmosphere. Permafrost is this ground that is permanently frozen year after year after year. That's melting. Storms produce more precipitation than they used to. We had a hurricane a couple years ago, Hurricane Harvey in Houston, Texas, produced in some places over 5 feet of rain, right? That's more than some of you are tall, 5 feet of rain in just a couple of days, in like 48, 72 hours, something like that. But as it warms up, there's more water vapor in the atmosphere. And the more water vapor there is in the atmosphere, the more fuel there is available for precipitation. So when it rains harder is a pretty robust forecast that we have, right? More floods into the future for most regions of the planet. Heat waves are more intense, right? As it warms up, your heat waves get more intense. We've been talking about a sixth mass extinction. So there's been 5 mass extinctions that have occurred over the history of the Earth, and this is a period of time when I think they define it to be that 75% of the species on the planet die during a mass extinction event. One, of course, was the dinosaurs becoming extinct because of an asteroid that hit the planet. So that's one that almost everybody has heard of. There's been 4 others, and people are talking about we're probably entering the Anthropocene is what we call this time right now, because just like anthropogenic is talking about human activities, right? The Anthropocene is this period of time now that we are in where the world is really heavily influenced by human activities. Okay, so come back to this overview slide for where we are, right? So I think we have talked all that I'm going to talk about with, like, is it warming, right? Is it warming? Yes, it is warming. And the warming is unequivocal. There's basically nobody in a climate denial camp today who is trying to argue that the world is not actually warming. The world is warming, and like everywhere that you look, there is evidence that the world is warming. So if you're in a climate denial camp, a global warming denial camp, then where you are is maybe attributing that warming. You're saying, well, maybe it's just natural variability, stuff like that. So the warming thus far has actually been a fairly small shift compared to what we expect in the future, and we'll talk about that in a future class. The next thing I want to talk about is why is it warming, and then after that we'll go on to the impacts of warming. And I think this is a good stopping spot, so I'm going to end this video here, and I will pick this back up, go get a drink of water, or just blow right through it. But it's always a good idea every 30 or 40 minutes to just take a mental break and come back. So that's